All right, welcome back. This is Chapter 7, Part B. When we left, we were talking about different things that are important with respect to moving air parcels. We talked about a list of them: pressure gradient force, Coriolis force, centripetal force, and friction. Now we're going to talk about the second one, Coriolis force, which is an apparent force that is caused by the rotation of Earth on its axis. Now that's why it's called an effect rather than a force in some textbooks. But to be consistent, since your textbook calls it Coriolis force, we're going to call it Coriolis force. Because the Earth spins on its axis, this causes free-moving objects to be deflected to the right of their intended path of motion in the northern hemisphere and to the left of their intended path of motion in the southern hemisphere. Now, for purposes of the discussion, air is considered to be a free-moving object in the Earth system. The amount of deviation in the path due to Coriolis of the moving air parcel is going to be much greater toward the poles and non-existent at the equator. There's no Coriolis at the equator. The farther north or south you go from the equator, the greater the deviation in the angle, to the right in the northern hemisphere, to the left in the southern hemisphere. The stronger the wind happens to be blowing, the greater that Coriolis deflection as well. Coriolis acts at right angles to the wind, but it only influences wind direction, not wind speed. I'm going to show you this interesting animation. It's a visualization that helps you see the effect of Coriolis. So if we click on that, you see a satellite picture. You see Canada and the Pacific Northwest and California. Now, without Coriolis, you would expect the predicted wind direction to be where the black arrow is going. In other words, air going directly from high pressure to low pressure, perpendicular to the lines of equal pressure, called isobars. Well, as I play this animation, you're going to find that that is, in reality, absolutely not the case. Because what happens is, it actually shows the air going more to the northeast. The black arrow, once again, shows predicted wind direction without Coriolis effect, directly from the high to the low. The actual wind direction is to the right angle of being deflected to the right of the intended path of motion. So I think this was actually a very instructive video for you. At least I certainly hope so. Remember back in your childhood when you went to the park and you spun around on the merry-go-round until you were dizzy? Well, this illustrates the Coriolis force. If you and a friend got on that merry-go-round and the merry-go-round was not yet moving and you threw a ball to your friend, obviously that person, your friend, would not have any problem catching the ball. But then you get that thing spinning around and around like crazy, and you throw the ball, it's highly likely that your friend is going to have great difficulty trying to catch that ball because relative to the spinning of the platform, the ball is going in a different direction. That's what Coriolis force is all about. This obviously becomes important in aviation, whether you're flying a commercial or military aircraft or even launching a missile. You want that object to go where you want it to go, to land at the airport you want it to. So in aviation, Coriolis has to be taken into account when the route of travel is determined. Let's talk a little bit more about another concept about why the wind blows, specifically referring to parcels of air aloft. Let's say we got a parcel of air and we get it to start moving, and it starts to rise into the atmosphere and starts to move. Initially, it moves toward low pressure because of pressure gradient force, and then immediately, once it starts to move toward low pressure because of PGF, it's acted upon immediately by Coriolis effect, and so the purple arrows indicate the resulting direction that the air parcel is moving toward. The parcel moves fast and high enough so that Coriolis, eventually when the parcel gets aloft, balances the pressure gradient force. The wind no longer accelerates because the net force is zero, and this is called the geostrophic or true wind. So basically, for parcels of air aloft, even though they're pulled toward low pressure by the pressure gradient force, they are pulled to the right by the Coriolis force, and the resulting wind direction is parallel to those contour lines we talked about in the upper air charts. Now, this is only an approximation of the real wind because in reality the contour lines are rarely straight or evenly spaced like the previous slide's example, and the wind changes speeds as it flows along. Obviously, if the air is made to be more constricted, just like a narrower riverbed, so to speak, then the wind is going to blow faster. The pressure gradient force increases, the Coriolis force increases, and the pressure gradient and the resulting wind speed increases if the channel is narrower. Air is a fluid just like water, so the same dynamics essentially apply. In the next figure, 17.8, winds are blowing at constant speeds but paralleled to the curved isobars. In this case, PGF, pressure gradient force, and Coriolis force again balance each other out. Why? Well, because aloft, the parcels of air are so high in the atmosphere that you do not have to account for friction with the Earth's surface at the boundary layer. The parcels are free to move without being impeded by the ocean surface or the land surface or valleys and so on. When winds blow around or a high or low pressure, when they are blowing parallel to these curved paths, they're called gradient winds. Centripetal force is the net force that is directed inward in this case so that the wind travels in a circle around either the high or the low. And this is the figure that explains this. Winds and related forces around areas of low pressure and high pressure above the friction level, meaning above the surface, aloft, way above your head. This is just for the northern hemisphere, though, not the southern hemisphere. Because in the southern hemisphere, winds blow around a low clockwise and around a high counterclockwise. It's the opposite. Speaking of that topic, the picture on the left shows you how wind flow goes into and around a low pressure counterclockwise in the northern hemisphere, and how wind flow and clouds around a low in the southern hemisphere move clockwise. It's just the opposite. On upper level charts, winds are depicted as moving parallel to those contour lines or lines of equal height. Or lines of the contour lines, we'll simply call them that. The winds in the upper atmosphere tend to travel in a wavy west-east pattern in the middle latitudes. Meaning that's where you live. Okay, Fresno is in the middle latitudes, 37 degrees north latitude. When the winds are oriented more north-south relative to the lines of longitude, we call the pattern meridional. When the winds are oriented more west to east relative to lines of latitude, we call that a zonal flow. So meridional flow is more north to south with the lines of longitude or meridians. West to east winds are called more zonal along the lines of latitude. On the chart depicted here, figure 7.20, winds at the 500 millibar level are shown. At that altitude, they move parallel to the isobars, or the contour lines, I should say. The solid gray lines are contours in meters above sea level, and the dashed red lines are isotherms, lines of equal temperature in degrees Celsius. Winds on a surface weather map, however, do not blow exactly parallel to the isobars. They cross the isobars moving from higher to lower pressure at weird angles, not at right angles, because you have to take into account Coriolis and also friction. The angle varies, but it averages around 30 degrees. The frictional drag of the ground, either dirt or the oceans, slow the wind down. This lower layer of air, where friction has to be considered, is called the friction layer or boundary layer. Near the surface, friction reduces the wind speed, which reduces the effect of Coriolis. So, the weaker Coriolis no longer balances the pressure gradient force like it did aloft when you didn't have to account for friction. And the winds blow across the isobars toward lower pressure in sort of weird angles toward the low pressure, or they blow away from a high pressure if that's the case. This map I've shown you before, but it shows a very intense low pressure system. And you can see how the wind sticks are not at right angles to the isobars. They're at weird angles, not just because of weakened Coriolis, but because of increased friction with the surface. This graphic, figure 7.21, shows the altitude of the friction layer and how it can vary somewhat. So if we're talking about the friction layer, we're talking roughly 1,000 meters or so above the surface. And once you get above that, in reality, it's more like 3,000 meters. Once you get that high above the surface, then you no longer have to account for friction on a moving air parcel, and the winds aloft then flow parallel to those contour lines, whereas the winds on the surface maps cross the isobars at these weird angles. It's also important to note that on the surface, as low pressure causes airstreams to converge toward the low, that air rises, and the only way that air can continue to rise is if there are separating airstreams aloft, and that's called divergence. Conversely, if you have airstreams slamming down onto the surface and spreading out associated with a surface high, that's divergence on the surface, that depends on convergence or airstreams coming together aloft. Winds converge toward a surface low, rise and diverge aloft. Winds converge toward an upper level low, sink and diverge on the surface. One depends on the other. Now, let's talk a little bit about extreme winds for a couple of minutes here. A small increase in the wind speed can greatly increase the wind force of an object. The force is roughly equal to v squared. For v, and v being velocity, of course. The amount of force exerted by the wind over an area increases as the square of the wind velocity. So, for example, if you're walking into a 20-mile-an-hour wind, that requires 4 times as much effort as walking into a 10-mile-an-hour wind. So keep that in mind on a particularly windy day when you're walking outside, or especially if you're riding a bicycle. That can be kind of rough if you're riding into the wind. The Beaufort scale, which is Table 7.2 on page 196, is convenient for gauging the effects of the wind with respect to giving you an idea of how the wind speeds go. Time does not permit to show you that here. You can look at it in your book. Now, let's talk about strong winds blowing over land. The book gives examples of a train in North Dakota in February of 1965, which the locomotive wasn't even on it, and the train started moving, and that's because the wind blew it. If you think about strong winds blowing over land, think about I-5, okay, in the western San Joaquin Valley, which I'll bet you anything this artist is trying to depict, because one of the co-authors of this book taught at Modesto City College. You get these winds that come across the coast ranges and then drop down onto the I-5 corridor in the western San Joaquin Valley. Those strong winds on the hillsides coming downslope adjacent to a roadway can produce a reverse flow of air from the opposite direction and make it very difficult for people who are driving trucks to control their vehicles. You can also get these weird effects called snow rollers. Strong winds going downhill can cause snowballs to form, and they get bigger and bigger and bigger as the strong winds force these snow rollers to go downhill. And then here's an example in Wyoming of what we call flag trees in the high mountains there, where the winds are blowing hard from one direction almost all the time, producing these trees where foliage seems to only grow favoring one side. Now let's talk about strong winds blowing over water. Ultimately, waves are caused by the wind, and waves that form by the wind blowing over the surface of the water are known as wind waves. How large these waves get is a function of how much energy is transferred to the water. That's going to depend on the wind speed, the length of time that the wind is blowing over the water, and the fetch or distance of deep water over which the wind blows. Figure X on the left side of this map shows the approximate location where a ship encountered 50-foot waves in the Pacific Ocean on January 6, 2005. That was a student research ship, and they got bounced all over the place, as you might imagine. A sustained 55-mile-an-hour wind blowing steadily for nearly 3 days over a distance of 1,600 miles can generate waves with an average height of nearly 50 feet. Wow. Even short-duration winds over a small area can cause havoc, like winds caused by a thunderstorm. February 28, 2009, along the Florida coast, a boat was capsized because of winds and a thunderstorm and high seas, causing, sadly, the drowning of 2 NFL players. Some of you sports fans might remember that. Water sloshing back and forth rhythmically due to strong winds blowing over a large lake are called seeches. And such waves occurred over Lake Michigan in December 1986 and again on Lake Erie in November of 2003. Here in California, we have these cold ocean currents from the Gulf of Alaska, which can cause strong currents of cold water to rise from the bottom of the ocean up toward the surface along our coast, and that's called upwelling. In this example, figure 7.29 shows how prevailing northwesterly winds along the California coast in summer allow for the cold upwelling of very cold water from the continental shelf up to the immediate California coast. Well, we've essentially run out of time on this PowerPoint, so what we need to do is tell you can look at the remaining slides on your own, and this ends Chapter 7b.